everyone, welcome back. Today we're going to do another example from this textbook. So the example that we're going to look at today is the Fibonacci number circuit in section 6.3.1. As you know, this circuit would generate a sequence of numbers where the first two would be 0 and 1, and then the third, the fourth, and so on would be the summation of the previous one according to this formula. So again, I assume that you have already read the textbook and you understood this ASMD chart for the Fibonacci circuit. So essentially comprised of three main states. In the first state, we initialize n with I, which is requested by the user as the number of Fibonacci numbers that would need to be generated, and really the generation is taking place in this up state of the ASMD chart, where register T1 would always contain and be assigned the contents of the previous two Fibonacci number values. And this is done as many times as necessary to generate the I first Fibonacci numbers from the Fibonacci series. The VHDL code for that is here in listing 6.4, which is the circuit that I wanted to test on the DE1-SoC board. For that, we need a testing circuit whose simplified block diagram is shown over here. Essentially, I'm instantiating the Fibonacci circuit from that listing from the textbook, which takes as an input the number I that will feed in through the slide switches on the board. This circuit will generate a sequence of Fibonacci numbers in binary, which will feed into a binary to BCD converter, which we saw previously in our previous examples, which will output up to 6 4-bit Fib5, Fib4, Fib3, and so on hexadecimal digits, and that will then convert into the necessary signals to drive the 6 7-segment displays on the DE1-SoC board. In addition, some very simple control that I'll show you quickly, and you'll be able to see by browsing the VHDL code, which is made available to you. Intel Altera PLL now instance over here to generate a 2 MHz clock signal, then which will be divided further to generate about 1 Hz clock signal that will feed into the Fibonacci circuit, because we wanted for these Fibonacci numbers to be generated quite slowly, so that we'll be able to display and look at them as they are shown on the 7-segment displays. That's pretty much it. I have already created here a Quartus project. You see here the top level design entity that will take the 50 MHz clock signal, a reset signal that will generate using the key 0 push button, the go input, and will show on a couple of LEDs, different bits of information. How many numbers, Fibonacci numbers we want for the Fibonacci circuit to generate, and then the outputs that will drive the 7-segment displays. There's a structural description that will instantiate a couple of components, as I showed you in that diagram, including the Fibonacci circuit, the binary to BCD converter shown over here, which will generate the 6 BCD outputs over here, each on 4 bits, the hexadecimal to 7-segment, which is showed before as the design entity in the Altera PLL, a couple of signals that you see over here, and the clock divider that is implemented as a very simple two-process description shown over here, which takes as an input the 2 MHz clock output of the my Altera PLL, and generates a tick every second, which will be used as a clock into the Fibonacci number generator that is instantiated over here, which also needs to generate the binary to BCD start signal that will signal the binary to BCD converter to start a new conversion, so that that new number will be correctly displayed onto the 7-segment displays. The Fibonacci number circuit is over here. It's essentially the one from the textbook with a slight modification to make it easy to generate that start signal that we need to pass to the binary to BCD. And that slight change is the addition of a new state shown over here, only for the purpose of having that signal that a new Fibonacci number is generated over here. That is pretty much the only change that we have to make to the Fibonacci circuit. Going back to the top level here, the only other components that we have are the 6 instances of the hexadecimal to 7-segment displays. That's pretty much it. So this top level diagram essentially implements this testing circuit for the Fibonacci circuit, where we have the slide switches telling the testing circuit how many Fibonacci numbers we wanted to have generated. So we set in the go. When we press the go, the generation will take place, and the numbers will be shown on the 7-segment displays that I'll show you in a minute. So I have already programmed the board. And you'll see here now the first 3 slide switches are set so that will tell the testing circuit that we want the first 7 Fibonacci numbers to be generated. So this is the reset signal, and this is the go. As you can see, 0, 1, 1, 3, 5, 8 are the first 7 numbers from the Fibonacci series. If I wanted to, for instance, generate 8 and not 7, I will set this 4th slide switch, and then everything else to 0, go, and then we'll see 0, 1, 1, 2, 3, 5, 8, 13 being the first. If I wanted one more, for instance, you'll see that we have one more Fibonacci number generated and listed there. Well, that's pretty much it. I hope this was clear.